Dear colleague, are you ready?
Yep.
Okay.
Good morning.
So it's my pleasure to open second day of our conference. I'd like to introduce first invited talk today, presented by Anton Podkopaev. So topic is very interesting and advanced. So Anton, are you ready?
Yep.
Okay.
Shall I start?
So
okay.
Let's go.
Sorry. Hello, my name is Anton Podkopaev. I would like to thank organizers for having me here. It's a great pleasure to give this talk in front of Circasi audience. A couple words about myself. I'm a researcher at JetBrains Research. I teach at Higher School of Economics in St. Petersburg. My research interests include programming languages, weak memory concurrency, compilation correctness proofs, functional programming, and actually on my day-to-day job, I do a lot of proofs, and usually they are mechanized in a proof assistant called COG. So it's still some code, but written in this unusual language. So I consider myself not being a software engineer, but being a proof engineer. I'm not going to talk much in this talk about COG, but I'll be more than happy to answer any questions regarding that if there will be any. So, something happened with my sharing. Just a second. Yeah, I'm sorry, I have a complicated infrastructure for giving a talk, since I'm doing it from my iPad, and for some reason it is broken. Okay. Oh, it's back. Yeah, sorry. Yeah, so getting back to the talk, it's about programming language memory models. So a couple words about the context. The talk is, in general, the field is shared memory concurrency, and this is the thing which is frequently used in high performance and critical applications, including operational system kernels, high performance libraries, and so on and so forth. Since it's used in such important applications, it is a critical task to be able to reason about programs, not only at the level of writing them by a developer, but also at the level of verifying them or writing different code analyzers to guarantee quality of the code. So to do that properly, you need to understand semantics of shared memory concurrency precisely. Without that, you may overlook some problems in critical applications, and it may lead to drastic problems. So here in the talk, I'll use the term memory model to define semantics of a concurrent system like CPU or programming language. In the previous keynote at Circasi yesterday, Dmitry was talking about memory models a bit as well, but in terms of representation memory in model checking, it's a different thing, even though the term, even though the term is used the same, but they are completely different things. So, if you check the title of my talk, there is memory model in plural form, so memory models. And I guess the essential question is, isn't there like the memory model, the semantics which explains concurrent behaviors? Why we need more than one? And actually, in some sense, there is the memory model proposed by Leslie Lampert in 1979 in a paper, how to make a multiprocessor computer that correctly executes multiprocess programs. And actually, the title somehow assumes that the problem is solved. It looks like we already from the end of 70s know how to define semantics of concurrent programs. However, as I'll show you, it's not completely true. So a couple of words about this semantics. It's called sequential consistency. In sequential consistency, all system behaviors, concurrent system behaviors, might be explained by sequential execution of interleaving of threads. So let's take a look at a very small example. So here we have a program. It starts with initializing x and y with zeros, and then it spawns 2 threads. In both threads, there are just 2 instructions. The first instruction is a write to a location, and the second instruction in the thread is a read from another location. Let's consider behaviors of this program under sequential consistency. So as I said, in sequential consistency, all behaviors are just might be explained by just sequential execution of interleaving of threads. Let's consider one of them. So here we have an interleaving corresponding to first doing the left thread and then doing the right one. Assuming that x and y are initialized with zeros, if we sequentially execute this code, it will lead to outcome a equals 0, b equals 1. I guess it's obvious, but just to make sure we're on the same page, in the beginning of the program, we have x and y being equal to 0. After doing this instruction, sequentially, we get x being equal to 1. Then we read from y, and we get the old value, 0. Then the write new value to y, it becomes 1. So then we read from x, and we read from this right, so we get result a equals 0, b equals 1. Obviously, this is not the only interleaving of threads of the program. So the other one is like this. So here, in opposed to the first one, we first execute the right thread and then the left one. So it starts with writing y to y, then reading from x, then writing 1 to x, and reading from y. So if we execute this code sequentially, we'll get a result a equals 1, b equals 0. Obviously, there are more interleavings. Actually, there are 4 of them. All of them correspond to the same outcome, a equals 1, b equals 1, since all of them start with writing 1 to x and y. And so as we see, there are just 6 interleavings which represent this program, and they may finish with one of the 3 outcomes on the slide. So under sequential consistency, all other behaviors of this program are disallowed. So for example, it's disallowed under sequential consistency to get result a equals 0, b equals 0. And this conclusion makes possible to use this snippet as a template for a mutual exclusion algorithm. So for example, we can add these ifs in the end. And since the result a equals 0, b equals 0 is prohibited, we may guarantee under sequential consistency that only one of critical sections is executed. Actually, there is also the case then none of the critical sections is executed. However, it's definitely not the case that two of them are executed. And actually, it's a slightly simplified version of Decker's lock. If I'll write this code in C or C++, compile it with GCC, and execute on my laptop with x86 architecture, I might observe that both critical sections are executed, meaning that there's some bug in this program. Decker's lock in this version doesn't work on a combination of the most common compiler and the most common architecture. And so what's the problem here? The problem is that both compiler and CPU are nowadays optimizing. They do different things to increase performance of the system. So one of the reasons is that GCC may reorder instructions in a thread. So for example, in the left thread, it may observe that X and Y are different locations, so accesses to them are independent, and it means that we can safely reorder it in the case of a single-threaded program. And this is how GCC actually does it. And unfortunately, I cannot show it now, but actually, I even have a Haber blog post about this example. Unfortunately, it's just in Russian, but I'll give a link to it later. And there is the C code you can download and try to execute on your laptop. And most likely, you'll get this behavior. And you'll see that GCC actually reorders these two instructions if it's being executed with -02 parameter. However, there are ways to forbid GCC from reordering these instructions. So actually, one of them is to insert empty assembly line between them, and this would forbid the reordering. But even if we do this, we still will be able to observe this strange behavior. Both critical sections are executed. And this is due to x86 architecture. So not only CPUs do optimizations, not only compilers do optimizations, but also CPUs. So actually in x86, there is a thing called write buffers, which actually uses as a buffer for writes. When a thread performs a write, it first goes to this buffer, and only at some point later, it is flushed to main memory. So for this particular example, it might be the case that the first thread, the left thread, performed the write to X and is already performing the read from Y, but the write to X is not yet observed by the write thread since it's buffered in first thread write buffer. And as I said, we can fix the first problem with GCC by forbidding GCC from reordering instructions. And actually, we can do this also for the CPU. For that, we'll have to insert a special instruction called mfence, which stands for memory fence. And it will require CPU to flush these write buffers. So it will forbid the behavior A equals 0, B equals 0 for this program. And it will fix the Decker's lock here. So, yeah.
Hello.
I'm sorry, someone doesn't turn his microphone. If you could do that.
Нет, ну не знаю, я выходил, ну, сказать, что...
Okay. Hey, Alexei, could you turn off microphone?
Не знаю, может быть, Клещи обычного. Он у тебя в зарядке просто. Вот.
Okay, I'll try to continue. Yeah, as I said, I have a Hubber blog post about this particular example with code which you can execute on your machines. So if you are interested, there is the link in the bottom of the slide. As we saw on real architectures and real compilers, we can observe behaviors which cannot be explained by sequential consistency. So such non-SC behaviors of concurrent systems are called weak behaviors. And concurrent semantics or memory models which allow weak behaviors, they are called weak memory models. And actually, it is the case that real systems, like all major CPU architectures and programming languages with concurrency, they all have weak memory models, since it provides since it doesn't restrict performance. And actually, it's a result of many optimizations which were implemented in compilers and CPUs in the days their multi-core CPUs were not so popular. And nowadays, we don't really want to turn them off, since it will slow down our single-threaded programs. So this is why we have to deal with weak behaviors nowadays. And one important thing to say that all of these concurrent systems, they all have slightly different semantics. And one of the hot topics nowadays is to do translation from x86 programs to ARM programs, since ARM architecture becomes popular in desktop. So for example, Apple introduced their computers with ARM CPUs. And if you want to move your x86 concurrent program to ARM, you actually have to do quite a lot, since ARM has much weaker behavior, much weaker memory model than x86. Especially if you do something especially if in your program you did something which goes beyond the standard of the language. So this is an important topic nowadays, and I heard from a number of companies that they try to do that. So for example, JetBrains, it has some things to do about this, since its main product, IntelliJ IDEA, developed in Java for Java virtual machine. On the surface, it looks like they don't have to do anything with transition to ARM, since they have this this overlay of Java memory model, but actually they do a lot of hacking in their code to increase performance. And the old assumption that IntelliJ IDEA was executed on x86 allowed to do that, but now if ones want to execute IntelliJ IDEA on ARM processors in Apple laptops, something has to be done about this. Okay, so now let's speak a bit about the, sorry, again, I have some problem with screen sharing. So there are two different groups of weak memory models. they are hardware memory models and programming language memory models, and they actually have slightly different requirements, constraints. Okay. So, for example, hardware memory models, the requirements we have for them is that they have to describe real CPUs we have in the wild. So a memory model, since it's a formalism which explains behaviors of concurrent system, it should be adequate to the things we have. And if there is some behavior allowed, which might be observed by real CPU, it should be inside of memory model, it should be allowed by it. Also, a memory model of hardware architecture, it should save some room for future optimizations. So for example, if Intel decides to make some optimization next year in their CPUs, it's better to be already allowed by a memory model we have now, or we'll have to rewrite our programs next year. And also, it should provide some reasonable guarantees for programming languages and developers. So they shouldn't be too weak. All right. So the first two requirements, they are kind of making a memory model weaker and weaker. We may say that a memory model allows all possible behaviors, anything, and then the first two requirements are resolved. But then it's impossible to write a program for such architecture. So this is why the third condition is important. On the other hand, for programming language memory models, we have slightly different requirements. So first of all, it should allow compiler optimizations. The second thing, supporting compiler optimization, for example, as we saw, it means that if we have a compiler like GCC and we want to use it, then a memory model of our language should support reordering of some type of instructions, as we saw for the Decker's lock. Also, a programming language memory model should allow way to efficiently compile to hardware. So if, as we'll see, if we want to enforce sequential consistency of the level of programming language standard, then we'll have to pay a big price for that at compilation, and it will slow down our programs. So as the first requirement, the second also tries to make a memory model weaker to allow more behaviors, at least allow behaviors which are observed on hardware. And the third one is, I guess it's not that understandable at this slide, but I'll say more about it later. And this is about having easy non-expert mode. So this is about saying that if your program is in some sense good enough, if it properly uses synchronization, then you may forget about some complicated aspects of a memory model. Also, it's not only important for developers. So it's not only important for developers, but also it's important for tool writers. So if you're writing some analyzer for the code, and if you want to assume something that, for example, there are no data races in your program, then you can simplify your tool drastically, and also you could not only simplify it, but also you can write a detector for some bad things in the program, and if they are detected, then you say, okay, there is a data race and it's bad, or otherwise you provide some great summary that everything is fine in the program, or you find some other bugs which are easier to find. So in this talk, we'll be talking about programming language memory models, their differences, and how they address these three criteria. Now I'll discuss these three in a more detail. So let's take a look at the first one, compiler optimizations. So suppose we have the program we already saw, this part of Decker's log, and suppose we want to be able to do the reordering of the instruction in the left thread I mentioned GCC is doing. Sorry, there is some lag for some reason, and okay, maybe. Okay. So there is the arrow, and this is in the bottom of the slide. Now we see an optimized version of the program. So if we want to support this compiler optimization, it means that in our weak memory model, the behaviors allowed for the program on the bottom should be also allowed for the program on the top. So here we use these square brackets, or also known as semantic brackets, to denote a function which takes a program in and give you a set of allowed outcomes. And as we saw, the set for optimized program should be included in the set for the original program. That would mean that this optimization is correct under the memory model. Now let's talk about the second condition. The second condition is about efficient compilation to hardware. And again, we saw, we'll discuss the same program we saw before. And suppose at the source level, at the level of programming language, we want to have sequential consistency. And suppose we want to compile our programs to x86 architecture. As we saw, to forbid weak behaviors and enforce sequential consistency, we'll have to insert special instructions, these memory fences. This means that we don't have fully efficient compilation to hardware to x86, since we'll have these instructions which are actually quite expensive to execute. For the purpose of this talk, I'll call such compilation schemes with fences non-optimal, and optimal compilation schemes to hardware would assume that we don't have any special instructions to be inserted in the program. So now let's talk about the third condition, the third requirement, this easy non-expert mode. And at the top level, it could be denoted as if you have a nice program, then you have only nice behaviors of that program. Usually for memory models, it means that if you don't have data races in your program, then you have only SC behaviors. And such thing is especially good if you have a slightly stronger version of it, not just random data races, but data races defined in terms of SC semantics, sequential consistency. Maybe you are aware of Java memory model, and in Java memory model, the definition of data race is related to some relation called happens before. And to use this mode in Java, you'd have to know happens before and Java memory model a bit to, since it is about data races in Java memory model. However, in general, we would like to have a mode as it's written here. So we need to know only the notion of data races in sequential consistency and nothing about the particular memory model. And then we'll be able to reason about programs just under sequential consistency. And this guarantee is called data race freedom guarantee. Many memory models try to provide that. So for example, here in this program, it's also quite small one, but slightly different. Now, instead of doing the write, we do the reads in the beginning of the program. And if we read something which is not non-initial writes, then we write to an opposite locations. So if we execute this program in sequential consistency, there are no data races. And not only there are no data races, also the only possible outcome of this program is A equals 0, B equals 0. Since there are no data races in HSE execution, in a memory model which guarantees data race freedom, the only outcome of this program is A equals 0, B equals 0. However, it's not the case for C++ memory model. So C++ memory model allows to get a result A equals B equals 1. And this is actually a problem which cannot be observed in real executions, but a problem of the C++ memory model formalism. And it has a special name. It's called out of thin air outcome. It's not the only example. There are much more complicated examples and some like the same level of complexity. And we'll discuss why C++ memory model allows this behavior and possible solutions for that in the remainder of the talk. So we saw the three main requirements: compilation optimizations, efficient compilation to hardware, and existence of DRF guarantee. So we'll consider the most popular memory models in terms of these requirements in this table. So as we saw, there are some memory models as rows in the table and the requirements as columns in this table. So I start with sequential consistency, Java memory model, and C++ memory model, as they are kind of the most well-known and highly used memory models. And first, let's consider HSE in terms of compilation optimizations. And as we saw, HSE doesn't support all compiler optimizations which could be done by common compilers like GCC. But still, it allows some compiler optimizations. So for example, HSE allows trace preserving transformations. So if you, for example, unroll the loop, then it's fine in terms of sequential consistency. It doesn't allow the reordering of normal memory accesses, as we saw in Decker's log example. And actually, a lot of things are allowed. I'm not going to define and explain all of them now, but if you want, I can do that in the question section after the talk. And now the question is, as we saw, there are not that many optimizations which are not supported by sequential consistency. What if we'll forbid a compiler from doing these particular optimizations? And actually, there is a study doing exactly that. There is a paper from 2011 which took LLVM and turned off optimizations which break sequential consistency. And it led to average slowdown of 34% on some benchmark, which included big projects. If we modify optimizations which break HSE to preserve sequential consistency, it leads to just 5.5% slowdown. So one may say that 5.5 is not that much. So maybe it's better to turn these optimizations off and modify the compiler to have this small slowdown. But actually, it doesn't solve the problem. Since it doesn't provide end-to-end sequential consistency. So as I said in the very beginning, these weak behaviors, they are due to two things, compilers and CPUs. And if we slow down our program at the level of CPU by forbidding some optimizations, it still doesn't guarantee sequential consistency. And also a drawback of this approach is that we have to modify existing compilers, and it's actually a lot of work. So getting back to the table, if we check the situation regarding Java memory model, confusedly, it even worse than with sequential consistency, in my opinion. And the problem is that Java memory model disallows some optimizations allowed by sequential consistency. So, for example, redundant read after read elimination is disallowed by Java memory model, which makes it impossible to do some common compare optimizations like common sub-expression elimination in Java memory model. And yeah, so and it's not only disallowed by Java memory model, but also it caused a trouble at some point, since even though it was forbidden by the standard, by Java memory model, it still have been implemented in the main Java memory model, in the main Java virtual machine in hotspot. And it meant that you may observe some behaviors on GVM which are not defined by the standard. Actually, it was a problem in 2008. I'm not sure if it's solved now. I don't know, but I think it's solved at the level of hotspot, not at the level of Java memory model. Okay, so now we need to see what's about C++, and actually C++ memory model allows quite a lot of compiler optimizations, and the situation there is much better than with Java and sequential consistency. So now let's go to the second column, to efficiency of compilation to hardware. And as we saw with SC, at least with compiling into x86, it's not that efficient. You have to insert some fences, but now let's discuss how bad is it, how much we lose by forcing sequential consistency. So there is some study which did that, and actually did via Java memory model, Java virtual machine, which provides some version of data race freedom I showed before. And instead of saying something about data races, it says that if all shared locations in your program are denoted as a volatile one, then you are guaranteed to have SC semantics. And there is a study which did exactly that. So they modified Java virtual machine to assume that all accesses are volatile. Actually, it's a bit more complicated if you look at the study, because they tried to do it in some clever fashion. So they also had some problems with arrays to be efficient and still provide these derived guarantees. But I'm not going to talk about these details today. If you are interested, please take a look at the paper, or we can try to discuss it after the talk. So, as I said, they modified Java virtual machine, and then they tested in two benchmarks. So there is this da Kappa benchmark, which includes big Java programs like Java implementation of Python, Jython. It also includes Eclipse, IDE, and many other big projects. And also the other set of benchmarks they tested this approach was a library called, some tests for a library called Apache Spark. As far as I know, it's some library for data science and machine learning related projects. So they tested this approach on x86 machine and two different ARM servers. And in the case of x86, it led to average slowdown of 28% on x86 at the Campo benchmarks, and with 81% of maximum slowdown. For Spark, the numbers are quite high. So average slowdown of the program was 79%, and more than 100% for Apache Spark. So as we saw, this is the cost. Approximately, this is the cost of enforcing end-to-end sequential consistency on x86 machine. And for some languages, it might be too high, but for others, it might be a reasonable price to pay. However, usually we write concurrent programs to increase our performance, so maybe we don't want to have even this slowdown, because then we may stick with single-threaded programs. For ARM, the numbers are actually even higher, since ARM is much weaker than x86. So, for example, if we take a look at the test for the first ARM platform, they get average slowdown of 57% on the Campo benchmark with 157% at max. For Apache Spark, the interesting is that the maximum slowdown was like extremely high. They don't even provide precise numbers in their paper, but it was more than 5,000% slowdown for Apache Spark. So the results for different ARM server are even higher, but comparable. So as we see, enforcing end-to-end sequential consistency on weak platforms like ARM is not obtainable. It's too high. Okay, so now we see that enforcing end-to-end sequential consistency on popular architectures nowadays is quite high. For Java and C++, the situation is better. So C++ could be compiled quite efficiently to hardware. And in the case of Java, they also tried to do this. They also wanted to have efficient compilation to hardware. But actually, the interesting bit that they get even too far with that. So if you take a look at Java memory model implementation for IBM Power, one of the popular architectures for servers, then you might find that they don't put enough these memory fences there. And this actually leads to breaking their own standard. And when we found with colleagues this problem, we discussed it with one of the members of Java standard committee. And the answer was that they are aware of this problem, but they still don't want to fix it, since it will slow down a lot of projects. So even though it contradicts the current standard. I don't have time to discuss this in detail in the main part of the talk, but I'll be happy to discuss it later. And regarding the third criteria, this DRF guarantee, it is actually obviously provided by sequential consistency, but not by Java memory model to some degree. But for C++ memory model, it is a problem. So as we saw the example with out of thin-air values, now actually I don't have that much time, but I'll try to briefly explain the problem. And actually this is where we get to the most technical part of the talk. So here we have the problem I said, which has a problem in C++ memory model. C++ allows to get the outcome A equals 1, B equals 1 for this program, even though it cannot be observed on modern architectures, even in combination with compiler optimizations. And to understand why the standard allows this behavior, let's take a look at slightly simplified version of this program. So here we get rid of control dependency in the left thread. And C++ memory model, it's a declarative memory model. It defines semantics of programs in terms of execution graphs. So one of them is presented on the slide. So actually, this graph, vertices in this graph are memory accesses. So here we have two read accesses to locations x and y, reading 0, and one write to y. It corresponds to execution. There we get the result a equals 0, b equals 0. And edges in this execution graph, they represent different relations on memory accesses. So for example, here there is only one edge, which is marked by PO. PO stands for program order, and it denotes program order between accesses in the left thread. So there are other executions under C++ memory model for this program. So one of them corresponds to result a equals 0, b equals 1. So here we also get 0 for the reading in the first thread. Then we do the write to y. And then the second thread, it observes this value. And this is why there is this read from or RF edge between the write and the read. So in the case we read 1, we perform the write to x. So this is how we get this value. And there is also the third execution, which corresponds to result a equals 1, b equals 1. And here we get this graph with a cycle, so of this shape. And this is behavior which you can get for IBM Power or for ARM if you execute this program. And the point there is that you may be able to reorder instructions in the first thread in these architectures. And actually, I should point out that this behavior is disallowed by x86 architecture, but still allowed by ARM. So if we want to efficiently compile C++ to ARM, we have to support this behavior for this program. So, and in C++ memory model, as I said, it's a declarative model, and there we construct these execution graphs, and then we check them with a set of axioms. And these axioms, they actually have a form of forbidding some cycles. So for example, they forbid cycles of the form PO and some subset of the RF relation, but not in this case. So this execution should be allowed as it's allowed on ARM. And the problem is that if we want to allow this execution graph for the program without control dependency on the left, since it's allowed for ARM, we have to allow this execution graph in general. So there is no way to write an axiom which will forbid it if it's related to the first program, but not to the second one. But we don't want to allow this behavior for the the second program on the slide. So the obvious difference between these programs is that there is a control dependency in the left thread in the second program. So what we could do is to add another relation to the graph, which will represent a dependency. And then we may do something like forbid cycles of the form PO control. Oh, sorry, not PO, but RF, right? What it will mean is that the first graph, it doesn't have such a cycle, so we allow it. But this one has a cycle of the form RF control, so we disallow it. However, this is the way hardware memory models solve this problem, but this is not how it's solved by programming language memory models if they want to support optimizations like constant propagation, for example. So, or others. So for example, here, if we slightly modify a program and now we have a control dependency, but the right to y is in both branches of if, we still can get the same execution graph as for the second program. We'll have this control dependency. But as we see, this is not real control dependency for the third program. So actually, it's like a fake control dependency. So C++ wants to allow such optimizations, and this is why it doesn't distinguish. It doesn't count dependencies because it's really hard to distinguish fake dependencies and real dependencies. But there are solutions for this problem. So one of them is to actually forbid all PRF cycles, and it will disallow all weak behaviors of the program in the previous slide. And there is a paper about this, and actually many papers about that. Actually, I'll skip a part of the talk, sorry. Since I don't have time for that. Yeah, and this solution with allowing PRF cycles, it is actually checked by colleagues for LLVM, and in LLVM, as always, to forbid some behaviors, we have to do two things: to modify a compiler and to maybe do something at the level of CPU to insert some instructions. So in terms of compiler optimizations, there was nothing to do in LLVM since it disallows reordering of reads and writes, and it was enough to forbid these PRF cycles. Yeah, sorry, I didn't have time to properly explain this part. Maybe I'll answer to questions related to this if there will be any, but the point is that we have to insert something between reads and writes, every read and every write. So on x86, actually, we don't have to do anything since these weak behaviors are disallowed there. For ARM architecture, we might insert bogus conditional branches to solve this problem. And this approach, it has an average slowdown of 0 for ARMv8 on some set of concurrent data structure benchmarks with maximum slowdown of 6.3%. So it means that this solution might be a good one for languages which allow some slowdown, but not, for example, for C++, and this is why it's not currently accepted by the C++ standard. Yep. But actually, there are some line of work which tries to properly distinguish semantics and syntactic dependencies. These models, they are quite interesting in the sense that they adopt a lot of ideas how to do that, and they are done in slightly different manners. So for example, promising semantics I've been working on for some time, specifically proving correctness of compilation from these two common CPU architectures. It uses very different approach comparing to C++. They have operational semantics, so defined in terms of abstract machine, to have these semantic dependencies. And as we see in the table, it has all smiling faces, so it solves a lot of problems, but still it has some restrictions. Yeah, and there are some other approaches. There are other memory models from other languages, like a camel memory model, which was recently proposed, which actually provide even more guarantees in terms of data race freedom. And JavaScript is also recently introduced shared memory concurrency, and has a memory model nowadays. And actually, it's quite close to C++ memory model. Many of these models are hard to explain and understand, especially the ones which try to have to distinguish semantics and syntactic dependencies. But still, there is some progress there. To take away from the talk, unfortunately, due to problems I had in the talk, I didn't have time to explain everything in detail. But the idea is that different memory models, they provide different compromises. So if you want to have maximal performance and to have zero-cost abstraction over hardware, then you have to go with complicated memory models like promising Weakestmo or MRD I showed. But if you may have some performance slowdown, for example, if you doing a language which is not supposed to be a system level language, then you can stick with simpler approaches. Yeah, I guess I don't have time to continue, so that's it. Thank you for your attention.
Okay, thank you very much. It seems, Anton, I understood many things before. It was a problem for me that your talk is very interesting and valuable for me at least. So do you have any questions?
Actually, I have a few very practical questions. So do you have open source formal memory models for well-known hardware architectures, for example, AIM and so on?
Sorry, which one you said?
ARM.
Yeah, actually the memory model of ARM is publicly available. It's part of the standard. It's defined in the, actually it has like two formalizations. One of them follows the one I briefly showed, declarative models like in C++. And actually they even have like, there is a framework called HERD, where it's like a common framework for defining these axiomatic or declarative memory models. And currently ARM provides a file in this framework as their standard for memory model.
Thank you. And one more question. So imagine that we have a new programming language and we develop a new memory model. So how much time, how much efforts does it take to formalize memory consistency? Approximately, I understand that there are different.
It depends on it depends on what you want to achieve. If you want to have a memory model with some nice properties, you can just take one of the memory models I showed here. And actually, it's like quite common approach, and then slightly modify it for your tasks. Actually, I'm in the middle of preparing. My colleagues and I are in the middle of preparing a paper with a section devoted to this, with some discussion how to choose a memory model. I hope it will be published at some point. But yeah, in general, it's not that hard. You just currently the idea is that there is some framework where you, like most of the models, they are defined over a language like C++ atomics, and then you just tick things you want to have, and yeah, this is how you get the memory model.
Okay, thank you.
Okay. Any questions?
Okay, thank you, Anton, for your very interesting talk. I really like it. So I have also a bit of practical question. Can we use this research in weak memory models to build some practical model checkers or deductive verifiers for example, programs in C++ with log-free structures and so on?
Thank you for your question. Actually, this is which I don't had time to discuss in the talk, but it's definitely should be said that there are model checkers for different memory models presented here. For like C++ memory model, as I showed with this out of thin air executions, it's impossible to do anything good in terms that you cannot have like model checker, proper model checker, which have this out of thin, which sorry. The problem is that if you have out of thin air behaviors, then you cannot reason about programs properly, and this is why you don't you cannot have like proper program logic or model checker. But if you assume some restriction of C++ memory model, for example, this C11, which I mentioned slightly, with pure of cycles being forbidden, then you can do quite a lot, and there are works doing that. Yeah, there are many model checkers for that. One of problems is that, for example, currently it's impossible to do modular analysis in memory models since there is no denotational semantics, which supports weak behaviors of ARM, power, and common compiler optimizations. But there is a work in this direction.
Thank you very much.
Thank you.
Okay, so it seems we finished the first talk. Thank you very much, Anton. Thank you very much for your questions.
Thank you.
So,